Okay, our final section here for the switching exam is related to wireless LANs and their interaction with the wired topology. Now, this section definitely is not a very large focus of the exam, so we're going to talk about, just from sort of a high-level overview, some of the concepts about how the 802.11 wireless networks work, and then also how some of the Cisco Unified Wireless System works, and the general design logic between the difference between the autonomous access points and the lightweight access points, and then how that could be used along with the Cisco wireless LAN controllers to integrate into the wired network. So this definitely is not going to be overall encompassing everything for wireless. As I mentioned earlier in the week, if you want more information on this, one of the really good books out there, it's a great resource, is the CWNA, the Certified Wireless Network Associate textbook that goes along with the CWNA certification. So you don't necessarily need to take the exam for it, but the title is just the CWNA official study guide. It's a really good one on general wireless stuff. So as we know with wireless, the goal here is that we are replacing the layer 1 topology from physical wired connections like our copper category 5 or category 6 cables or fiber optic cables with the RF media, the wireless media. Okay, when we're talking about 802.11 and Wi-Fi, we're also replacing the layer 2 or data link layer transport for the network. So whereas Ethernet takes care of the data link and the LLC, the two sublayers, the MAC and the LLC, in wireless, we're going to have a different layer 2. So Wi-Fi technically is not wireless Ethernet. It has its own layer 2 specification. The frame formats and how the management is done in layer 2 is different than Ethernet. Now, people usually don't make that distinction if they don't know a lot about wireless, because wireless also uses MAC addressing, layer 2 MAC addresses, just like Ethernet does. But technically, it's not wired. It's not wireless Ethernet. And you'd see that if you looked at like a capture of an 802.11 frame in a packet analyzer versus the capture of an 802.3 frame or an Ethernet 2 frame from the wired network. So we still use MAC addresses, and like legacy Ethernet, wireless is a shared media. So basically, the access point in the network is acting like a multi-port repeater or a hub. Okay, we talked about this previously. The differences between a hub and a switch is that everyone on the hub is in the same collision domain and in the same broadcast domain. So this implies that the communication for wireless is half duplex and collisions can occur. So there is no such thing as full duplex wireless. Okay, some vendors use that as marketing terms to talk about multiple radios, and especially with the new 802.11n specification for the MIMO, or the multiple input, multiple output, which basically means we have multiple antennas. Technically, that still is not full duplex. Okay, all Wi-Fi, all 802.11 sub-specifications are always going to be half duplex. Now, with Ethernet, we know that half duplex is dealt with by running the algorithm known as CSMACD, or Carrier Sense Multiple Access with Collision Detection. Now, in Ethernet, this basically means that before we transmit a frame, we need to listen on the physical wire to see if someone else is talking or someone else is transmitting. Okay, the listening period is known as the contention window. So we're trying to contend, or we're fighting for the physical wire in order to make a transmission. Now, if someone is transmitting when we listen, while we're listening during this contention window, we're going to go through a basic backoff algorithm that says we're going to wait a certain amount of nanoseconds or microseconds before we try to check the wire again. Now, for whenever we check the wire and someone else is not transmitting, then we can encapsulate the frame onto the wire and send. Now, in the case that it happens that two stations listen to the wire at the same exact moment and both find it free. This is the case where a collision occurs. So two stations, maybe they're on opposite ends of the network. So they're there's physical distance between them on the wire. So they both transmit onto the physical link. The signals are going to run into each other and they're going to get corrupted. This is what we consider a collision. Now, when this happens, there will be a jam signal sent out to all stations in the collision domain, basically telling them that they have to wait longer before they transmit. So it's basically an alert, an error message that goes out to everyone that says whoever just sent caused a collision. Now everybody has to wait an additional backoff period before they run the contention algorithm again. So this is going to happen over and over and over in a loop for every single frame that you want to put on the Ethernet wire. Okay, this is why, like I mentioned previously, even though legacy Ethernet has a maximum capability of 10 megabits per second, you're never going to get that high in a practical application, because a bunch of bandwidth is going to be taken up by the amount of time it takes you to run this CSMA CD algorithm, and then bandwidth is going to be taken up by collisions that occur, and then the time the jam signal is sent, and the time that you need to back off. Now, in today's wired LANs, this is not an issue, because we know nowadays we run our links in full duplex mode with switches, where there are only two devices in the collision domain. It's the transmitting host and the receiving switch port, or the transmitting switch port and the receiving host. Now, since with the physical wiring of twisted pair or with fiber optics, there's a difference between the send channel and the receive channel. So when I send a frame, it's down a different physical wire than it is on receive. In full duplex mode, we don't need to run this contention algorithm. So CSMA CD is only used for half duplex Ethernet. Now, Wi-Fi or wireless LANs or 802.11 doesn't have this luxury, because the air itself, the radio frequencies, the wireless media, is shared between whoever can transmit a wireless signal. So there's no physical cabling that can separate the send channel versus the receive channel for the devices that want to send. So anybody that is in range of your wireless signal is technically within your collision domain. So whether they're actually running Wi-Fi or whether it's some sort of source of interference, like a cordless phone or a microwave or like a baby monitor, basically anything that is in the 2.4 gigahertz range or the 5 gigahertz range could be technically within your collision domain. So with Wi-Fi, we run into this logic problem. Okay, we cannot listen while we're sending, because there's no difference between the send channel and the receive channel. It's just the air that we're trying to transmit on. So this also means that we cannot listen for a jam signal. So the actual radio that we're using is half duplex. You're either sending or listening. You can't do both at the same time. So this is one logic problem we run into. We cannot hear the jam signal. We need to figure out some other way of detecting the collisions. Okay, there's also a possible problem that in the world of Wi-Fi is known as the hidden terminal problem. Now, this basically means that we have 3 or more devices that are on the wireless media, so they're within range of each other. And host A is in range of B and C, but B and C are not in range of each other. So what we can end up in this type of scenario is that host B thinks that it's okay to send, and host C thinks that it's okay to send, because they cannot hear each other's transmissions. But the guy in the middle, A, knows that both B and C are sending at the same time, and neither signal is going to be received properly. So to make sure that there's no interference, we need to make sure that only one station that is within range of the other ones is sending at a time. Now, the specific implementation they came up with to fix this is known as carrier sense multiple access with collision avoidance. Now, the key difference being that with Ethernet, we are using collision detection, whereas with Wi-Fi, we are using collision avoidance. And it uses a feature that is known as the distributed coordinated function, or DCF, in order to run basically a random timing algorithm to figure out, if no one is currently sending, how much time should I wait before I can build my layer 2 frame and then send it out onto the to the wireless media. Now, once I send the frame out, since I cannot listen at the same time I am sending, I need some mechanism besides the jam signal to figure out if a collision actually happens. The way that Wi-Fi implements this is that for every single frame you send, okay, with the minor exception of some control frames, that's going to be outside of our scope, but with every data frame that you send, it must be acknowledged by the access point. So this is why when we hear that the technologies like 802.11b has a maximum rate of 11 megabits per second, but effectively it is 5.5, it's because the media is shared and it is half duplex. Okay, the vast majority of traffic actually in a Wi-Fi network is going to be acknowledgments and retransmissions and all sorts of stuff that is stopping you from getting very high up into that transmission range. So even with the new standards with the 802.11n, it's something crazy like 800 megabits per second is the maximum transmission rate, but there's so much interference and there's so many retransmissions going on that your effective rate goes down to like 100 megabits per second under the best possible cases scenario. So it's a little bit misleading when you look at some of the vendor marketing information, which is going to be true whether we're talking about 802.11a, b, g, or n. They're all going to have this shortcoming that they have to run the CSMA-CA algorithm, or the carrier sense multiple access with collision avoidance. Now, if we send the frame and we do not receive an acknowledgement, then it is up to the sending station to retransmit. So this means that it could be the actual wireless host, like your laptop with your Wi-Fi card, or it could be the access point itself. So if something comes off the wired LAN down to the AP is trying to send it to the laptop, and the laptop does not acknowledge, the access point is going to buffer that up and keep trying to retransmit it until either the traffic is successfully transmitted or until it times out and the packet is going to have to be dropped. Okay, so this actual function that we are running, the distributed coordinated function, or the DCF, is the actual implementation of how the collision avoidance works. Okay, and the logic of it is fairly straightforward. First off, it says if we are a wireless client and we want to send out onto the RF, first thing we're going to do is listen. We're going to listen on the particular channel that we are tuned into. So if we are running 802.11b, it's going to be some channel that's in the 2.4 gigahertz range. Versus if we're 802.11g, then we're going to be somewhere in the 5 gigahertz range, maybe 5.5, give or take. So we listen on which particular channel that we are tuned into. If no one is transmitting, we're going to send our frame. But along with the frame, we're going to tell everyone else how long it physically takes us to send that to the destination and to get an acknowledgement. So this is going to be a function of how long the frame is, plus some basic padding to figure out how long it's going to take them to process it and how much time it's going to take to get back. It's going to be a very, very small amount of time regardless. It's going to be a few microseconds, because we're looking at very, very fast transmission rates. So along with the frame, we tell everyone else it's going to take me 10 microseconds, for example, to send this. Now, if someone else is listening and they heard me sending, they are now going to look at that duration field and wait. They're going to wait until the duration expires, plus an additional delay, which is defined by a random backoff. Okay, so let's say that we listen onto the wire and we hear that someone else is transmitting. So we hear their frame and we figure out their duration. Let's say that this is 10 microseconds. Okay, they also sometimes call these ticks, so 10 ticks. It would be 10 time intervals. So we're going to wait for whatever that value is, plus an inter-frame spacing. which is called the Distributed Coordinated Function Interframe Spacing, or the DIFS. A DIFS is basically some additional padding to make sure that we're really giving them enough time for the frame to get there and then for the acknowledgement to happen. So at a minimum, everybody has to wait at least the duration plus the DIFS. But in addition to this, everyone figures out a random backoff time or a random amount of ticks that they're going to wait in addition to the duration and the interframe spacing. So let's say, for example, that I listen onto the media, which is the air. So I listen to the air. I hear that someone is sending and their duration is 10. So I wait 10 ticks. I wait whatever the DIFS is. It's going to be based on the individual specification. So it'll be different in 802.11b versus 802.11g. I wait the interframe spacing. Then I calculate a random tick value of 5 ticks. That's going to be my next duration. Or that is my random backoff. So I waited 10 plus the frame spacing plus another 5. Once the 5 expires, then I can listen again to see if the air is free or someone else is transmitting. So the idea behind this is that since the backoff algorithm is random, it's unlikely that two stations are going to choose the same exact value and end up transmitting at the same exact time. Now, it does happen from time to time. There are collisions, and this is why we have the additional function that the AP needs to acknowledge every single frame. So if we don't get the acknowledgement back in, we're assuming that for some reason it was lost, whether it was a collision or just some sort of other interference that's out there in the air. Okay, so here we have an example. We have 3 hosts, host A, B, and C. All of them are trying to send traffic onto the RF. So first off, host A listens and it sees that no one is currently sending. So it builds its packet, sends the frame out. Inside the header, we're advertising the duration. In this case, the duration is X, plus the Distributed Coordinated Function Interframe Spacing, the DIFS, is Y. Now, very, very shortly after A sends its frame, B starts listening. B wants to send a frame as well. So B hears A's packet and says, I have to wait at least X plus Y, the duration of the frame plus the spacing, plus a random backup. So I'm picking some random value Z. Host C does the same thing at the same exact time. So host C says, I have to wait X plus Y, the duration plus the interframe spacing, plus some random backup that I'm choosing. Now, who gets to send next depends on which device chose the lower random backoff. So if host B chose a value that was lower than C, then host B ends up to send next. If host C sends a value or chooses a value less than B, C is going to send next. If they choose the same value, which is unlikely but still possible, if B's random backoff and C's random backoff end up being the same, then the collision is going to occur. So it's kind of interesting how this is implemented in the different the standards. One of the newest specifications that is a modification for this is wireless QoS, which basically says that if you are a high priority station, your interval for the random backoff is shorter than other people. Because with the RF media being the air, there's really no way to prioritize one station sending over the other. What you're doing in wireless QoS is basically allowing them to cheat when they're running the distributed coordinated function. So you're giving them a shorter interval that they have to wait after the minimum wait time, which is always the duration plus the distributed interframe spacing. So of course, just like Ethernet, this is the stuff that's happening behind the scenes. It's unlikely that you would ever need to really verify this or troubleshoot this in the real world. But it is interesting to know how the specification works versus Ethernet, because this is just one example why Wi-Fi is not wireless Ethernet. It's its own complete layer 2 implementation. Okay, next topic we have in the layer 2 header for wireless LANs is the SSID, or the Service Set Identifier. Now, in Ethernet LANs, we know the devices that we can talk to directly at layer 2 will be defined by our broadcast domain, which is essentially our VLAN. So if two hosts are in the same VLAN, they can send broadcast traffic directly between each other. But with wireless, technically everybody is in the same broadcast domain. So if I set up a network at my office, Brian McGann Wireless Network, and there's some next door neighbor that also has wireless, there's nothing stopping him from grabbing my frames out of the air or vice versa. Because we're all in the same broadcast domain, we're all in the same collision domain. And what's actually interesting is that even if the devices are not in the same SSID, everyone still runs the distributed coordinated function together. So if I hear my next door neighbor's wireless signal, my laptop is actually contending with them in order to send traffic out into the air. So the SSID on its own doesn't really have anything to do with the collision domain or the broadcast domain. It's just a logical value that we are using to figure out which devices are going to associate with the access point. It doesn't control any of the traffic segmentation. Now, in the SSID, there's a couple sub-terms that can get confusing, and a lot of the documentation uses this not necessarily incorrectly, but they make it a little bit more complicated than it needs to be. Okay, the key is that there is a difference between the SSID, which we would normally think of like SSID, Cisco, or Tsunami for whatever we're associating with the access point, and what is known as the Basic Service Set Identifier or the Extended Service Set Identifier, the BSS or the ESS. Now, the way that this works is that every device will always have an independent BSS, the Basic Service Set. Okay, the Basic Service Set is basically their MAC address. So it's the layer 2 address on the segment. The SSID is going to be the ASCII value that we would normally think of the SSID that we're trying to define as the association. Okay, but within that association, there's a couple different modes that we can run in, which would be considered the independent basic service set, the basic service set, or the extended service set. Now, the first one, the IBSS, this is what we would consider the ad hoc mode, where you have two wireless clients that are trying to talk to each other without using an access point. So they have a single association with each other. They're listening for frames just based on each other's MAC addresses. Now, the basic service set would be considered the infrastructure mode, where we have multiple clients associated with a single access point. So maybe we have 10 laptops and cordless phones and all sorts of stuff in your house. They're all associated with the same access point. This would be considered a basic service set. The extended service set is when there are wireless clients that are associated with multiple access points that share the same SSID. So this is the case that is typical for an enterprise deployment. Typically in your office, you're not going to have just one access point that is servicing everybody. You're going to have multiple access points that have the same SSID, but they use different BSSIDs, which is effectively their MAC address, to distinguish themselves inside the extended service set. So in the extended service set, the SSID overlaps, but the BSSID never overlaps. That's going to be the unique MAC address that is associated with the AP itself. Now, the ESS, the extended service set, this also allows us to do some advanced applications with wireless, one of them mainly being transparent roaming. So as the client disassociates with one access point and reassociates with another, the goal is that we want it to be transparent from the application's perspective. Okay, the most extreme case of this for roaming would be like if you have a Wi-Fi phone. that if you're on your wireless phone and you're walking throughout the office, you disassociate with one access point and reassociate with the other one. You don't want to have to drop your phone call. So that would be transparent layer 2 roaming from the wireless handsets point of view. So in the Wi-Fi world, to send traffic into the network, first thing we need to do is set up what's known as an association. An association is basically an agreement between the client and the access point that they're going to listen to each other's MAC addresses and they're going to deliver traffic back and forth on each other's behalf. The way that the association occurs is generally, first off, the client sends out what is known as a probe request. A probe request would be like when you open up Windows and you view the wireless networks locally and you see all the SSIDs that are located. Okay, so this is a control frame known as a probe request. It's the client trying to figure out who are all the access points that are out there. Okay, this is also where you would tell your access point not to broadcast its SSID. It means that when the access point responds with the probe response, you would simply not put the SSID value in there. So it technically will still respond, and if you were running a wireless sniffer like Wild Packets or Sniffer Wireless, you still actually would be able to see all the information from the access point going back and forth. Because remember, the key for wireless here is that everyone is in the same broadcast domain, everybody's in the same collision domain. So if you're running a wireless sniffer, you can pull everybody's traffic out of the air, not just the devices that are in your local AP's association, okay, or your local cell, what they call it. Okay, so first the client sends the probe request. The AP responds with a probe response. So it's the asking for the access point is answering. Okay, there's also another possible progression for this where the access point started with an unsolicited beacon, which is basically a keep alive. If the client hears the beacon, then it knows that that access point is available for association. So the client starts the association, which is going to be made up of some authentication steps. If the access point accepts it, it's going to install their MAC address into what is effectively the CAM table. Now, we're not going to go into details with the actual association and the authentication, because it depends on what particular parameters that you're trying to run with the AP. So if you're running TKIP with AES for running wireless, the wired privacy authentication, then it's going to be different if you are running like WEP, for example. So that type of stuff is going to be outside of our scope. Okay, but in any case, when we're talking about wireless in the enterprise, that's always going to be the first step, that the client is forming the association with the access point. Now, the access point's job normally is to move traffic from the wired network to the wireless network, or to grab traffic from the wireless network and then repeat it back out. So either wired to wireless or wireless to wireless. Now, in order to do this, there's a couple different roles that the AP can take. The first one is going to be a bridge. Okay, this is normally what we would think the access point as. So it takes traffic from the LAN, so from the wired network, and it forwards it out to the wireless network. Now, it's similar to how a switch would work in the fact that it is a transparent bridge. So it's not modifying any of the layer 3 options. But actually, let me take that back. It technically would not be a transparent bridge. It would be a translational bridge, because we are decapsulating our Ethernet frames as they come in the LAN, and we are re-encapsulating them as 802.11 frames, because the layer 2 packet formats are different between Ethernet and the Wi-Fi. But in either case, we're taking the traffic in the wired network, and then we are repeating it out the wireless network. Now, you can also do this in a point-to-point manner, which in the case, those devices are called workgroup bridges instead of being access points, or point to multipoint. which would be for, let's say, 3 buildings, and you're trying to use wireless on top of the buildings in order to build a basically like a full mesh of communication between them. Okay, next would be a wireless repeater, where you basically just accept the RF signal in and you send it back out. This would be some sort of wireless range extender. So you're not doing any modification to the frame, you're just receiving it in and then repeating it back out. You're trying to just basically increase the strength of the signal. Now the third one, the mesh topology, which is a relatively new feature that is getting pretty popular in the wireless world, is a combination of both of them at the same time. Okay, mesh topologies today a lot of times are used for outdoor wireless networks. Like in a university setting, you could use a mesh topology to give Wi-Fi to the quad area, like the big open space between the buildings, where some of the access points may be connected to the wired LAN, but not all of them. So they act as both bridges and repeaters to try to get as much coverage as possible, but then to also be fault tolerant for each other. So if one goes down, the other ones are going to pick up the slack for it, and then to do advanced features like roaming and load distribution. So visually here as a multi-point bridge, this is typically what we think of when we're talking about an access point. So traffic is coming in from the wired LAN, and then we're sending it out to the wireless media, or vice versa, it's coming in the wireless media and then we are sending it to the wired LAN. Now, if these two access points here were sharing the same SSID, this is what we would consider as an extended service set, an ESS. Now, each of these APs would have a unique BSS ID, which is the basic service set identifier, which again is basically their MAC address. So this is how the host actually figures out which access point am I talking to, by the BSS ID. The SSID is for the association, then the ESS is the description of the multiple APs. So definitely it can get confusing because they keep reusing this term over and over, SSID, but in different usages it has different meanings. Okay, next we have the point-to-point bridging topology. This would be like between 2 buildings, point-to-point. You're trying to bridge with like a directional antenna on the top of the roof. So traffic comes in the wired LAN. We are sending it out the RF to the other bridge, and then it's being bridged back in to the wired LAN. Now, not all access points support this. Most of the time, you'd have to buy a particular device that's listed as a workgroup bridge. This is also when you go to the local electronics store and you see those wireless game adapters. That's basically what they're doing. They're doing workgroup bridging. So they're receiving the RF signal in and then bridging it back onto the wired LAN. Okay, here we have the wireless repeater. So the repeater on the left here, it does not have a connection to the rest of the wired infrastructure. So we are receiving the RF signal in and then just repeating it back out to the rest of the network. Okay, there's a bunch of design limitations when you do this type of setup, where the range is greatly reduced by the repeater. Usually the general recommendation is that if you do wireless repeating, you need 50% overlap of the cells. So it basically means that the APs would have to be pretty close to each other in order to get the same amount of coverage. Okay, then lastly we have the wireless mesh topology. So you can see that some of the devices, for example, the AP on the bottom right, this has a connection to the wired network, but the rest of them are just receiving the signal in and then repeating it back to everybody else. So it's a complex set of point-to-multipoint associations where the ultimate goal is that we're trying to cover as much space as possible and also add redundancy. So it's interesting how the actual implementation of this works. The APs become intelligent where they know who are all the other access points in the mesh group. then for example, if one of them goes down, let's say this one on the bottom left goes down, the APs can automatically increase their power output to try to fill the gap of the coverage that of the AP that left the mesh group. So it's a relatively new design. It's really neat what you can do with some of these mesh topologies nowadays. Okay, this question: do the access points need to be in the same channel for this instance? For each point-to-point association, they would need to be. Now, some access points can run multiple channels at the same time because they have multiple radios. So if you have multiple 802.11g radios, it means that we could run one channel between these two guys and then run a second channel between these two guys. And as long as they're non-overlapping channels, then there would not be a problem with the interference between them. So it really depends on the individual platform. Usually this type of setup, as you can imagine, it's pretty expensive to do. Okay, the next feature we have for what we would consider an enterprise access point like AeroNet, as opposed to your consumer grade AP like a Linksys box, is that we have wireless VLAN support. Basically what this means is that an SSID will correspond to a VLAN by trunking back to the wired LAN. Now, again, don't get confused with the terminology here because technically everybody is still in the same broadcast domain and still in the same collision domain. So even if we are in different wireless VLANs, we're in different wireless SSIDs, we still have to run that same contention algorithm with each other, and we can receive each other's traffic. Okay, this is why in a wireless topology you always want to make sure that you're running encryption, like you're doing WPA2, because otherwise anyone can just run a wireless sniffer and get any of your info out of the air. So with the wireless VLANs, basically what we're doing is specifying that based on the SSID, the different VLANs have different properties. So we could say that VLAN 10 with the SSID guest, it has just open access. But VLAN 20 with SSID private, it has WPA2. So when we connect back to the rest of the physical topology, there's going to be an 802.1q trunk link between the AP and then between the layer 2 switch that's connecting it back to the LAN. So people in SSID guest for VLAN 10, they would be in the same IP subnet, same as the SSID private. But all four of the devices, all four of the clients here, technically they're all still in the same collision domain, they're all still in the same broadcast domain. Okay, next here we have Cisco's new implementation of this with their product lines. This is known as the Cisco Unified Wireless Solution, or the CUWS. This basically means, long story short, that we are adding more intelligence to the management of the Wi-Fi network. Now, in previous designs, access points that are standalone and take their own configuration are now called autonomous APs. So if you buy a Linksys AP from Best Buy, that's going to be an autonomous AP. It means that if you want to configure an SSID on it, you want to configure parameters, you need to do that configuration locally. Now, the unified wireless solution is interesting because we're decoupling the management of the wireless network from the actual physical layer RF transmission and some of the layer 2 management. We're separating it into two different modules, what we call a split MAC design, where the access points are called lightweight access points, or LWAPs, and the wireless LAN controller, or the WLC, is responsible for administering all of the access points in the network. Now, what's interesting about this is that the wireless LAN controller is in charge of all the configurations for all the APs in the network. Or in larger designs, you would have clusters of LAN controllers that service a subset of different access points. But the AP itself basically has no configuration, and it's used just to do the actual RF transmission and then the control plane stuff. So like sending beacons, sending probes, and doing any sort of packet buffering. So the lightweight access point cannot exist in the network without the wireless LAN controller. The wireless LAN controller tells the AP what its SSIDs are, what the VLANs are, who it should be associating with, what are the authentication parameters, what are the QoS parameters, etc. So what's really nice about this is that once the wireless LAN controller is set up, you can go anywhere in the network that has a wired connectivity, plug an AP into that port. The AP can potentially automatically find the wireless LAN controller, download the configuration from the WLC, and then immediately start servicing wireless clients. So in very large topologies where you need to keep adding access points in order to add more coverage, it's very plug and play from an administrative point of view. So once the wireless LAN controller is properly configured, you just plug the AP in. It can learn everything from either the controller directly or from other access points, which is, they use the term over-the-air provisioning, or OAP. Now, the actual traffic flow when we're using the lightweight access points and the wireless LAN controllers, it's a little bit different than you would think of a normal wireless topology, where with an autonomous AP, we just have the traffic being bridged in the Ethernet port of the access point and then being repeated basically out onto the RF media. But with the lightweight access points and the wireless LAN controllers, we use a layer 2 or layer 3 tunneling mechanism between them that is known as the lightweight access point protocol, or LWAP. Okay, there are some other minor variations of how the tunneling works, but the logic is still going to be the same. Basically means that all of the data that is coming from the access point or going to the access point is going to be tunneled inside of these new special tunneling frames, the lightweight access point protocol tunneling. Now in layer 2 mode, this is kind of considered legacy. It's not supported on a lot of the newer platforms. It means that the wireless LAN controller and the access points, they're on the same VLAN and in the same subnet. They have to be somewhere in the same flat layer 2 network. The second design, which would be layer 3 LWAP, lightweight access point protocol, basically means that as long as the access point can reach the wireless LAN controller anywhere through IP, then it doesn't matter where the LAN controller is located. So this gives you a more centralized design where you can still separate the layer 2 and layer 3 network to make sure you don't have a huge broadcast domain, but the management still stays at the wireless LAN controller. So here in a layer 2 LWAP topology, traffic comes in on the AP, and it is tunneled up to the controller. Okay, once it gets to the controller, then it can go back down either to the rest of the IP network or down to another AP for transmission. With the layer 3 LWAP, this access point would be on a different subnet than the controller, 20.0.0.0/24. And as long as we have IP reachability between these two devices, it's going to be fine, because it's going to be tunneled inside a UDP, inside the LWAP tunnel. So it means that you can put your wireless LAN controllers in some sort of centralized location that has good connectivity to the rest of the network. And as long as you can route down to where the access point is located, you eventually will get there. So like I said, for this particular exam, the new switching exam in CCNP, wireless is really not that big of a topic focus. You do want to understand some basic general concepts about 802.11 itself, and then like the differences between the autonomous APs and the lightweight access points, where again, autonomous is standalone. The configuration is saved directly on the AP. With the lightweight access point, you don't console into the AP, you don't configure anything directly. You just make sure that it can talk to the wireless LAN controller, and then all the configuration and management is downloaded from there. So from here, if you do want to get more information on wireless, Like I mentioned, the CWNA, the Certified Wireless Network Administrator book is really good. Also, there's a Cisco Press book for CCNA Wireless that has some good information also about how the Cisco Unified Wireless Network solution works.